So the paper that I'll be presenting on is called GDF-15 promotes the proliferation of cervical cancer cells by phosphorylating AKT1 and ERK1-2 through the receptor ERBB2. So what is cervical cancer? It is a cancer that starts when cells in the body begin to grow out of control. Cervical cancer starts in the cells lining the cervix, which is the lower part of the uterus known as the womb. This is sometimes called the uterine cervix. The fetus grows on the body of the uterus, which is the upper part, and the cervix connects the body of the uterus to the vagina. So the cervix has two different parts and is covered with two different types of cells. The part of the cervix closest to the body of the uterus is called the endocervix, which is seen here, and is covered with glandular cells. The part next to the vagina is the exocervix, which is seen here, also known as the ectocervix, and is covered in squamous cells. These two cell types meet at a place called the transformation zone, and the exact location of the transformation zone changes as you get older and if you give birth. Most cervical cancers begins in the cells in the transformation zone. These cells do not suddenly change into cancer. Instead, the normal cells of the cervix first gradually develop precancerous changes that turn into cancer. So, types of cervical cancer. Most, up to roughly 90%, cervical cancers are squamous cell carcinomas. These cancers develop from cells in the exocervix, and the cancer cells have the features of squamous cells under the microscope. Squamous cell carcinomas most often begin in the transformation zone. Most of the other cervical cancers are adenocarcinomas. Adenocarcinomas are cancers that develop from gland cells. Cervical adenocarcinoma develops from the mucus-producing gland cells of the endocervix. Adenocarcinomas seem to be more prevalent in the past 20 to 30 years. Less commonly, cervical cancers have features of both squamous cell carcinomas and adenocarcinomas. These are called adenosquamous carcinomas or mixed carcinomas. Although almost all cervical cancers are either squamous cell carcinomas or adenocarcinomas, other types of cancer can also develop in the cervix. These other types, such as melanoma, sarcoma, and lymphoma, occur more commonly in other parts of the body. So at a glance, about 13,240 new cases of invasive cervical cancer will be diagnosed, which is equivalent to 0.8%, and about 4,170 women will die from cervical cancer, which is roughly 0.7%. Cervical precancers are diagnosed far more often than invasive cervical cancer. Cervical cancer was once the most common causes of cancer death for American women. The cervical cancer death rate dropped significantly with the increased use of the Pap test, which is a screening procedure that can find changes in the cervix before cancer develops. It can also find cervical cancer early, when it's small and easier to cure, but it has not changed much over the last 15 years. Cervical cancer tends to occur in midlife and is most frequently diagnosed in women between the ages of 35 and 44. It rarely develops in women younger than 20. Many older women do not realize the risk of developing cervical cancer is still present as they age. More than 15% of cases of cervical cancer are found in women over 65. However, these cancers rarely occur in women who have been getting regular tests to screen for cervical cancer before they were 65. In the United States, Hispanic women are most likely to get cervical cancer, followed by African Americans, Asians, and Pacific Islanders, and then whites. American Indians and Alaska Natives have the lowest risk of cervical cancer in this country. So, it's a little background. Growth differentiation factor 15 is a member of the TGF-beta superfamily. Along with being upregulated during inflammation and injury, there is evidence that it plays an important role in carcinogenesis-related activities, including proliferation, migration, invasion, and angiogenesis in various types of tumors. So the aim of the study, and the article titled Gene Expression Changes During HPV-Mediated Carcinogenesis, a comparison between the in vitro cell model and cervical cancer, GDF-15 was identified as a novel potential biomarker of cervical cancer. Unfortunately, there is no evidence demonstrating the effects of GDF-15 expression on development and progression of cervical carcinoma. The molecular mechanisms of GDF-15 and cervical carcinoma are also largely unknown. This study aimed to fully explore the function and mechanisms of GDF-15 and cervical carcinogenesis. So the first result, Although GDF15 expression has been discovered in various carcinomas, its role in cervical cancer is not well defined. To investigate GDF15 protein expression in human cervical carcinoma, immunohistochemistry was performed in normal cervix, high-grade squamous, intraepithelial lesion, and squamous cervical cancer tissues. In Figure A, GDF15 was classified into two categories, positive and negative. Figure B then quantifies the data where positive GDF15 staining was found in 38.1% of normal cervix samples, 69.6% of the high-grade squamous intraepithelial lesion samples, and 78.1% of the squamous cervical cancer tissues. Figure C represents the immunoreactivity scores obtained for GDF15 staining in NC-HCl and SCC samples. The average IHC scores for GDF15 were 2.95 in NC cells, 5.09 in HSIL samples, and 5.84 in SCC. With SCC having the highest score, it indicates that the greater magnitude of staining. In a follow-up study performed with TCGA database, women with high GDF15 expression showed a statistically significant higher risk of cancer development and shorter disease-free survival time within 10 years compared to women with low GDF15 expression. These data suggested that GDF15 has evolved in the development and progression of cervical carcinoma. With that data, Figure D shows the expression of GDF15 in 8 samples of normal cervix and 10 samples of cervical carcinoma. Figure E illustrates that the relative expression levels of GDF15 in these cervical carcinoma tissues were higher than that in normal cervix. Conclusively, these results are all suggested that GDF15 was highly expressed in the examined cervical cancer specimens and may be involved in the process of cervical carcinoma. In a previous study, a relatively high level of GDF15 expression was detected in HT-3 cells, but relatively low expression of GDF15 was observed in HeLa, SIHA, C33A, and Kaski cells. The function of GDF15 was investigated in cervical cancer cells by adding recombinant human GDF15 and human serum albumin to the media of HeLa and SIHA. The cell growth curves in an MTT assay were evaluated to the proliferation and viability of HeLa and SIHA lines. As shown in figures A and B, HeLa and SIHA cells treated with rhGDF15 grew more rapidly than their controls. Figures C and D illustrated that the viability of HeLa and SIHA cells treated with recombinant human GDF15 was much higher than respective controls. An MTT study showed that 50% conditional median significantly increased in proliferation of HeLa GFP and SIHA GFP cells after treatment for 96 hours. Figures E through H, in a converse manner, illustrate that GDF15 knockdown in HT3 cells using both CRISPR, Cas9, mediated gene editing, and shRNA technologies resulted in significant decreases in cell growth and viability. The combination of these results demonstrated that GDF15 protein stimulated the proliferation of cervical cancers in vitro and in both an autocrine and paracrine manner. To further demonstrate the effects of GDF15 on tumor formation ability in vivo, 6 adult female nude mice in each group were subcutaneously transplanted with HeLa GDF15 or SIHA GDF15 their control cells, as shown in figures M and N. In figures I and J, the xenograft assay in Balb-C nude mice show that GDF15 overexpressing cells formed much larger tumors. In terms of volume, where figures K and L show that GDF15 overexpressing cells formed much larger tumors in terms of weight than the control cells HeLa GFP and SIHA GFP. Furthermore, IIT revealed that xenograft tumor tissues formed by HeLa GDF15 and SIHA GDF15 cells demonstrated much stronger Ki-67 staining score than those formed by control cells in figures O, P, Q, and R. Figures O and P represent the immunohistochemical staining results for Ki-67 tumor xenografts of GDF15 overexpressing HeLa and SIHA cells, where figures Q and R exhibit the quantitative analysis. Together, these data suggest that GDF15 promoted tumor formation of cervical cancer cells. To investigate whether GDF15 affected the cell cycle of cervical cancer cells, flow cytometry was performed to analyze differences in the cell cycle between GDF15 modified cervical cancer cells and their control cells. In figures A and B, the percentage of cells in G0 and G1 phase obviously decreased from 59.3% in HeLa GFP cells to 36.4% in HeLa GDF15 cells, while the percentage of cells in S phase was markedly increased from 30.5% in HeLa GFP cells to 50.1% in HeLa GDF15 cells. In figures C and D, a consistent similar result was observed in CHA cells, but the percentage of cells in G0 and G1 phase decreased from 70.9% in CHA GFP cells to 53.2% in CHA GDF15 cells, and the percentage of cells in S phase increased from 20.8% in CHA GFP cells to 35.8% in CHA GDF15 cells. These results suggested that the overexpression of GDF15 accelerated the cell cycle transition from G0, G1 to S phase cervical cancer cells. In figures E and F, the percentage of G0, G1 cells significantly increased, and percentage of S phase cells significantly decreased in HT3 SH-GDF15 cells compared with HT3 SH-NC cells, was suggested that GDF15 silencing delayed the cell cycle transition from G0, G1 to S phase. Together, these results showed that GDF15 accelerated the cell cycle in cervical cancer cells at the transition from G1, G0 to S phase, and suggested that GDF15 promoted cervical cell proliferation through alterations in the cell cycle phases. To explore the detailed mechanisms underlying the effects of GDF15 on cell cycle, real-time PCR and Western blotting were applied to verify the key cell cycle regulators in GDF15 overexpressing cells and their control cells. In figures A and B, CDC2, CDC258, CDK2, CDK4, and cyclin D1 mRNA was expressed at much higher levels in HeLa GDF15 and CHA GDF15 cells than in their control counterparts. In figures C, D, and E, cyclin D1 and cyclin E1 proteins are also expressed at much higher levels in both HeLa GDF15 and CHA GDF15 cells than in their control counterparts. They also showed the decreased expression of FOXO1 and their increased expression of CMYC, both HeLa GDF15 and CHA GDF15 cells compared with their respective controls. These results strongly suggested that GDF15 accelerated cell cycle progression in cervical cancer cells by targeting CDC258, CDK2, CDK4, P21, cyclin D1, and cyclin E1 through alterations in the expression of FOXO1 and CY-MYC. In sum, the expression of P21 was significantly decreased at both the mRNA and protein levels in both HeLa GDF15 and CHA GDF15 cells compared with their respective controls. Figures F and G illustrate that pro-GDF15 expression was further elevated after treatment with conditional medium from GDF15 overexpressing cells and treatment with recombinant human GDF15. The authors speculated that there was a mechanism regulating the positive feedback of GDF15 expression. In figure H, a quantitative chromatin immunoprecipitation assay was applied to demonstrate that CY-MYC recognized and bound the promoter to transactivate the expression of GDF15, and figure I demonstrated the positive feedback between GDF15 and C-MYC. In the previous study, inhibition of PI3K-AKT and MAPK-ERK pathways causes activation of FOX, a transcription factor leading to cell cycle arrest in apoptosis and pancreatic cancer. It has been demonstrated that the expression of FOXO1 and C-MYC is regulated by AKT1 ERK1-2 through the PI3-AKT and MAPK-ERK signaling pathways in various human carcinomas. In this study, the expression levels of PI3K, AKT1, PAKT1, ERK1, ERK1-2, and RAS-GTP were detected by various Western blotting or immunoprecipitation assay. Figures A through D, there is an increase in the expression of PI3K, PAKT1, PRK1, PRK2, and RAS-GTP in both HeLa and CHA cells. Figures E, F, G, and H show that GDF15 knockdown in HT3 cells by CRISPR technology and by shRNA decreased the expression of PI3K, PAKT1, PRK1, PRK2, and RAS-GTP compared with HT3 CRISPR-NC and HT3 SHNC cells. All of these data suggest that GDF15 promoted cervical cancer cell proliferation and tumor formation via activation of the PI3K and AKT and MAP ERK signaling pathways. And the study macrophage inhibitory cytokine 1 activates AKT and ERK1, ERK2 via the transactivation of ERB2 in human breast and gastric cancer cells. It was shown that ERB2 is transactivated by GDF15 in human breast and gastric cancer cells. And figures A and B in MTTSA demonstrate that HeLa and CHA cell proliferation was significantly promoted by our recombinant human GDF15 administration, but was inhibited by treatment with an AKT inhibitor or an ARK1, ERK2 inhibitor. Furthermore, both the TGF-beta-R inhibitor and the ERB2 inhibitor significantly suppress the proliferation of HeLa and CHA cells, but the ERB2 inhibitor had a more potent inhibitory role than the TGF-beta-R inhibitor. In figure C, D, and E, the Western blotting results showed that the expression of PAKT1 and PRK2 was decreased by the ERB2 inhibitor treatment, but not by TGF-beta inhibitor treatment HeLa and CHA cells. Figures F, G, and H, the expression of PAKT1, PRK1, PRK2, and C and YC was much lower in HeLa SH ERB2 and CHA SH ERB2 cells than HeLa SH NC and CHA SH NC cells. Figure I, via immune precipitation assay, showed that GDF15 bound to P ERB2 in both HeLa GDF15 and CHA GDF15 cells. Together, these results suggest that GDF15 activated the PI3K-AKT and MAPK-ERK signaling pathways through ERB2 in cervical cancer cells. To validate the correlation between the expression of GDF15 and PI3K-AKT and MAPK-ERK signaling related protein cervical cancer specimens, the expression of GDF15, PAKT1, PRK1, PRK2, COMC, and FOXO1 was detected by I8C in figure A. So a Pearson correlation analysis showed that GDF15 expression positively correlated with the expression of PAKT1, PRK1, PRK2, and CYMC in 16 cervical cancer cells with R-squared values of 0.54, 0.27, and 0.42, and p-values of 0.002, 0.0048, and 0.009 respectively, and for figures B, C, and D. However, the expression of GDF15 negatively correlated with the expression of FOXO1 with R-squared value 0.31 and p-value of 0.033 in figure E. These results indicate that GDF15 was associated with the increased activity of the PI3K-AKT and MAPK-ERK signaling pathways in human cervical cancer. So, in conclusion, the data demonstrated that GDF15 promoted the proliferation of cervical cancer cells via the upregulation of cyclin D1 and cyclin E1 and the downregulation of P21 through both the PI3K, AKT, and MAPK ERK signaling pathways in a complex with ERB2.